Hello everyone, this is Narges from University of Klagenfurt. I would like today to present our accepted paper with the name of the CNN-assisted road sign inspection on the computing continuum. Unfortunately, because of the visa procedure, but I could not travel to be present in that conference to have the presentation in person and also to meet the researchers and scientists at the UCC conference. So accept please my apologies and I hope that you will find this presentation interesting. So this is Narges, a PhD student, a doctoral student at the University of Klagenfurt. And on my name and on behalf of my supervisor's name, I would like to present our paper. Firstly, let me to introduce the main topic of the paper by considering the main motivation for the paper. Then I will talk about the main aspect of the application, which is regarding the road sign inspection, and specifically we have targeted the CNN-based or CNN assisted-based application with the abbreviations that stands for convolutional neural network-based application. Then I will talk about the one specific application placement architecture with the name of the CODA, and then I will continue with the experimental setup, the conclusion, and then at the end some possibilities for the future work. Modern data processing encompasses complex workflows, as you can see in this figure, that encompass different number of components, tasks, or mainly based on whatever today we have microservices that can be matched to different number of containers. So each one of these tasks have different requirements. Maybe they need some data to be gathered in order to start their processing. Maybe they need to store data multiple times and read and write from some specific storage device or volumes. And also, along with that, they need some sort of processing analysis that requires different amount of computation, not only the communication aspect, but also the computational requirement, which have overwhelmed the cloud data centers, although still they're capable of processing that. That's why the idea of utilizing the computing continuum consisting of different layers of these computational devices from the cloud at the top connecting to the lower layers such as the fog, which are we can call from this type of infrastructure as a service, such as the Exascale Edge, or Exascale is a European cloud provider, or the Google distributed cloud, or even Amazon has approached by providing the wavelengths for the 5G based applications. And also the Cisco has provided some sort of functionalities in order for the users to run specific VMs to run their applications. These sort of services are open source, of course. And from the other side also we have the lowest layer that are the edge layers, and this edge layer has this functionality to process or to pre-process maybe for some sort of anomaly detection before sending the main data to the higher levels or tiers of the computing continuum. From the other side, considering the applications that can be deployed over this computing continuum, one of the attractive ones is the autonomous driving, which is slowly becoming a reality in today's world, considering that there are different cameras, such as the ones that you can observe in this figure. So mainly two cameras are attached to the front of the car or maybe to the dashboard of the car, and then they can bring the view from the front or the this viewpoint from the front of the car, along with, for example, different sensors that are attached to the side of the car, such as the horse that can see the left and the right side. So they can bring also the viewpoint from the left and right, along with other type of sensors, such as GPS and other things. So it can be a good motivation to consider um, to approach to designation of an application, which is a road sign inspection or traffic sign recognition, because of the automating of the inspection and recognition uh, of the traffic the traffic that the car, or maybe the autonomous car, or the manual driving cars are going to. Traffic inventories as a tool in today's world aims to provide an insight from the state of the roads. What do we mean specifically in this work by the state of the road? To detect the anomalies of maybe traffic signs or the road signs. Maybe these traffic signs are broken, covered, worn out, or maybe incorrectly, or maybe have been erased. One specific thing that we didn't target in this work was those traffic signs that have been stolen, of course, when they are not there, so we could not recognize them. But yeah, the other type of traffic signs that maybe have been covered or worn out, we have tried to inspect. We target specifically the machine learning based, encoding based, and framing based type of applications in order to be deployed over the computing continuum, consisting of, for example, the cloud data centers that has been sliced into different instances that can be provided to the users, connected throughout the topology of the internet to the fog, to the edge, maybe those micro data centers that are directly connected to the base stations, or maybe femto data center, femto base stations, I mean, so femtocells. And at the lowest layer, we have this sort of single board computers, or maybe a little bit high performance computers that are capable within the specific amount of time to store the data for the users and also to do the processing. From the other side, there is this type of application that can get the data from one specific sensor, such as the camera, which sends in terms of different number of frames, and then there is this compression or encoding, and then maybe some sort of framing that can be done by utilizing one library such as OpenCV, and then the machine learning or deep learning based frameworks that can be applied in order to train a specific model over a specific data set, and then later on to test them. Well, up to now, the state of the art have mainly targeted the inference-based model, and in conjunction with the encoding and then the framing was something that we were trying to explore in this work. So considering that a video stream is being fed into the system or the application, it consists of different frames. Maybe inside one frame there is one traffic sign, such as, for example, 20 kilometers per hour speed limitation. So we try to encode firstly with the high resolution this video stream, and then through the framing we try to make the video into a smaller frame. It depends on the quality of the video. Maybe at the end the sizes would be different, and then we would apply some sort of machine learning based applications. Firstly, we would train the model based on a specific data set. Here we utilize the German traffic sign a data set consisting of 43 different number of traffic signs. And then we utilize this machine learning inference in order to save the model later on for some sort of testing. For some users, maybe it's really helpful because it takes less amount of time in order to process and test maybe one specific frame that they want to detect and recognize or inspect. And then at the end, we applied some sort of packaging that can provide these traffic signs for the consideration of the driver of a car. It can be a voice or something, but here in this work it was specifically for us one picture or one frame. If you have noticed and if you have observed, there are some sort of cues here because of the asynchronous type of communication between each one of these services, task or microservices that we have in this application. So that maybe if there are multiple videos that are being fed into the system, so they will be pushed into the queue, and then one by one, that service will pull them, start to starts to process them, and then later on to transmit them to the other components such as the framing. The framing also does the same for the training and so on and so on. Please let me to explain, because of the lack of time, two specific components of such an application that we have designed. One of them is the encoding one. As the name comes, the encoding component or task receives the raw video and then tries to encode it or transcode it maybe into different bit rates with different resolutions. Um, Specifically, we have used the codec H.264 as it is really popular nowadays in the community of the video compression. You can observe the bitrate in the radar consisting of different pairs of the bitrate and resolution, and specifically we have targeted 5 different pairs of the bitrate and resolution from the lowest to the highest bitrate. And the tool that and the framework that we have used is the FFmpeg software suite for encoding the video with different qualities, as you can observe in this figure. Then the next one that I would like to explain at the moment for your consideration is the CNN model, or the training or machine learning model that we have used in this work. The training model consists of a multi-class model. So at the end, it will gives us as the output one specific traffic sign that has been detected. Because the input, because the dataset consists of 43 different classes of the traffic signs, that's why the output will be provided from one of these values, and the probability that to which class it is closer will be provided for us. The accuracy of the model was around 90 to 95%, and then the dataset consists of around 50,000 different still frames. There were two different convolutional layers, as can be observed. The first layer has a depth of 6, and then the input to this layer consists of the frames with the size of the 32 multiplied by the 32 and 1. And then this layer has the output, because of the configuration of it, that it will be provided in the with the size of the 28 multiplied by 28 by multiplied by 6. And then this layer, which is the max pooling layer, will fit this data to another convolutional layer. All of these layers have all of these convolutional layers for us have the activation function of the ReLU. And the second convolutional layer will provide, which has a depth of 16, will provide the images of the size 10 multiplied by 10. And then at the end, one max pooling will be applied, which provides a smaller data for us. and then at the end the multiple fully connected layers will be applied. You can observe that at the beginning the output is 400, then it would be 120, then 40, 84, and then at the end 43 because of the different number of classes that we have. Then the last step is a softmax that provides a probability for us that to which category, to which class exactly one of these images um, is related to. You can observe the layers, the inputs, the convolution or max pooling, the activations, and at the end the softmax and the description of each layer in this table for your consideration. Regarding the application, we have provided the application and we have mainly Dockerize or containerize each one of the tasks of this application. Because of the architecture of different machines that are available, we categorize them into two different machines. So one of them is x68 and then the other one are the ARM-based machine. Because, for example, the Raspberry Pi or I don't know, the Jetson Nano devices are mainly from this type of architecture. Although nowadays, and recently I understood that there is this possibility to use, for example, some commands like Docker manifest, which provides this functionality to have different layers of the different Docker images so that with just one command you can run it regardless of what sort of architecture you are using. So it can maybe merge the same Docker images that has been provided and prepared for different type of architectures. All of these images are provided in the Docker Hub repository for your consideration. But how about the application placement model that I mentioned that we have applied to this sort of application? This architecture consists of different components. Mainly, these components receive the workflow and also some monitoring information that has been gathered from the computing devices in the computing continuum in different layers that I mentioned in the first slide. Getting this information, receiving this information, firstly we have this ranking of the task and also of the devices. So we considered a game between the task of the application and also the devices in the computing continuum. And then this ranking, when this ranking is done, we applied a matching so that these tasks will be matched to the specific devices to start their execution later on. Please let me bring a small example for your consideration. So as I said, in one side we have the task, considering that at the moment we have 5 different number of tasks. Each task tries to rank the devices on the other side. On the other side, we have 5 different devices on the computing continuum. So for example, task 1 has ranked D1 with the highest rank, and then task T2 has ranked D4 with the highest rank. On the other side, also, the devices have ranked the tasks one after the other. Maybe, for example, you can find one task that has not ranked one of the devices because it does not satisfy its requirement based on the architecture that we have designed, such as the lower computing and processing time. So now that this ranking has been finished, the next step starts, which is the matching for us in this step. And based on the ranking that the rank that each device has, so the task starts to find the suitable match. At the end of the game, as you may observe, the tasks are matched and then you cannot find any other matching for a specific task or device than their current preferences that have been matched to. For example, T1 has been matched to D1 because D1 also has ranked previously T1 in its preference list. Because D1 has a higher capacity in terms of the computation or maybe the networking capacity and resources that it has, then D1 can host more number of tasks. That's why also D1 has accepted the execution of another task, which is T3, because T3 has also previously ranked D1 in its highest, with the highest rank, and also D1 has ranked T3 with the highest rank. So if you observe, D1 has been matched to two options that it has selected from its preferences. Also, it happens for the other devices. D2 does not get any task because the task prefers other resources than D2, unfortunately. But at the end, because all the tasks have been matched to the devices in this computing continuum, then the application will start its execution. In order to evaluate our work, we considered the C3 testbed and the URL of it you can find in the slides. This testbed consists of single board computers, as you can observe in this picture, and they are interconnected through an open flow switch to a high performance machine, and then this machine is connected to the exascale European cloud instances consisting of large, medium, and small type of instances located in Sofia, Frankfurt, Vienna, and Klagenfurt for us. We considered Sofia because of the further distances of it as the cloud instance for us. We modeled it as the cloud, and the Klagenfurt as the edge because mainly our universities resided also in the Klagenfurt. The result that we have obtained and also we have evaluated our work are based on the completion time and the CO2 emissions. We compared our work, which is CODA for this application that has been processed, this CNN-based application, compared with the CLIP, one of those approaches that also they have considered the traffic-based applications to be processed and placed over the computing continuum and mainly the edge devices, and then another approach which is KCSS, which is Kubernetes container-based scheduling strategy. KCSS mainly targets the cloud instances, such as, for example, the Google, the AWS, or also this exascale cloud. So it targets to place the applications over one specific clusters, which maybe they are farther than the source of the data. However, CLIP targets the communication between the application components and maybe put all the application components over one specific device, which may be overwhelmed one device, but at the end it will try to reduce the time of the execution time and also the amount of CO2 that will be emitted, which is directly connected to the energy consumption of the resources. The energy for regarding the CO2 emission, this this parameter or this metric is directly connected or directly related to the transmission and processing time of a workflow execution. And meanwhile, we have considered one and evaluated one specific metric, which is the equivalency of 1 kilowatt per hour of the CO2 of the energy that is being consumed, which is equivalent to 620 grams of the CO2 which can be emitted in the world. or in the atmosphere, we can say. Our approach mainly had superiority in comparison to the state of the art, specifically for different bit rates that have been selected for the encoding. So, coming to the end of this presentation, in this presentation, firstly, I introduced the main motivation for this paper that has been presented for your consideration. I explained and described the CNN or convolutional neural network assisted application, mainly targeted for the road sign inspection. Then I explained about the type of the placement algorithm, application placement algorithm CODA, that has been applied to this sort of application to be placed over the computing continuum, and then the evaluation specifically targeted at the um, completion time, the CO2 emission, and also the data traffic intensity. For the future work, there is this possibility of extending the work because all of these sensors or camera sensors have captured the data from one specific angle. Maybe different angles of preparation of the data set can be explored, or maybe from multiple perspective and angles. These videos or these images can be captured. And also regarding the CNN or convolutional neural network, it can be one good focus in order to explore the lightweight models so that really it can be processed over the single board computers. And also we plan to explore the object recognition model so that it will be added to our model and it will be explored, so we can check the energy consumption because of the one of the project that in the following slides I will explain is the Gaia. So we want to explore also this aspect to inspect, for example, with different qualities, how the training will be applied, and then what will be the energy consumption for us considering these object recognitions. And we plan to really explore deeper this aspect. Also, there are other projects that have funded um, uh, our work. One of them is the Corinthian Fog project, which is an FFG or Austrian-based fundraiser for our work, and then the other one is the European Cloud Data Cloud. That the main goal of it is the execution of the big data pipeline over the computing continuum. At the end, I would like to attract your attention to visit the application that has been designed over the GitHub repository. Thanks a lot.